Jai Hind students, welcome to this particular session. In the previous lecture, we have derived lens formula for convex lens, both when the image nature was real as well as when the nature of the image obtained was virtual, right? In this particular lecture, first and foremost, we'll try to derive the lens formula for concave lens. And students, as you are aware, in the case of concave lens, the image obtained is always on the same side as that of the object. What I mean to say is that image is always virtual, erect, and it is diminished, right? So let's start with the mathematical derivation of lens formula. So suppose this is the concave mirror. This is the concave lens actually. This is the concave lens, which is thin at the center and thick at the edges. This is the optical center and this is the reference line. This is the reference line. And suppose this is the principal axis, right? Let us consider this to be focus. This is the virtual focus of this concave lens. An object may be placed anywhere. Wherever the object may be placed in front of a concave lens, the nature of the image obtained is always virtual, erect and diminished, formed on the same side as that of the object. Suppose the object is placed over here. Suppose this is the object. This is an erect object placed over here. AB. Its height is h1. Size of the object is h1. Look, this is it. First rule. As for the first rule, the ray which is parallel to the principal axis, after refraction, it will appear as if it is coming from the focus. So it will be like this. So if you produce it in the backward direction, it will appear as if it is coming from the focus, right? So that is the very reason why concave lens is also known as a diverging lens. And students, what's the second rule? Second rule is incident ray while passing through the optical center of the lens will remain undeviated. It won't get any sort of bending, right? So its path will remain undeviated. So it's like this. Its path will remain undeviated. So this is the intersection of dotted line and dark line. So here, if you drop a perpendicular, this virtual erect diminished image would be obtained. This is A dash and this is B dash. Clear students? We have already done this particular topic of the image formation in case of concave lens. This again, I am repeating this particular topic. Suppose this point is N. Now this ray being parallel to the principal axis, these are the perpendicular distances, so it will be same. And we will proceed in this similar manner. Like we need to consider two pair of triangles, we need to prove that they are similar, the corresponding sides are proportional, right? So let's proceed with a similar manner. So let's consider triangle AOB, AOB. I am considering this triangle, and consider triangle A dash OB dash. I am considering triangle AOB and triangle A dash OB dash, the smaller one. Look students, this will be the common angle. This is 90 degree, this is also 90 degree. So these two triangles are definitely similar. Therefore, their corresponding sides must be proportional. So let's consider A dash B dash. The corresponding side of A dash B dash is AB. The corresponding side of OB dash of the smaller triangle is OB in the bigger one. So you can put it as equation number 1. So that's the first pair of triangle. And they are similar, therefore their corresponding sides are proportional. We have to find the other pair of triangles as well, right? So what we'll do is, we can consider these two triangles. Look, MFO, this is one of the triangle, and A dash FB dash. So I am considering these two triangles, MFO, this triangle, and A dash FB dash. So again, this would be the common angle, and this is 90 degree, and this is also 90 degree. Therefore, triangle A dash FB dash must be similar to triangle MFO. A dash FB dash must be similar to triangle MFO. Right? So the corresponding sides are proportional. Again students, please ensure that the left hand side should be same. So A dash B dash A dash B dash, its corresponding side would be MO. And students, MO, it's equal to AB. So that the left hand side of these two equations becomes equal. It is equal to, now consider base of the smaller triangle. So base is B dash F. Divided by, of this triangle, the base is OF. Right? So, from equation 1 and 2, it's pretty clear that the left hand side are equal, therefore we can equate the right hand side. So therefore, from 1 and 2, we get OB dash divided by OB is equal to B dash F divided by OF. Now as we are all aware, all the distances are to be measured from the optical center. So initial letter, initial alphabet should be O. So no problem with these three terms, but B dash F needs to be changed. This is B dash F, B dash F. This can be written as OF minus OB dash. B dash F may be written as OF minus OB dash. So what we get is OB dash divided by OB is equal to B dash F is OF minus OB dash. Right? Now let's make use of sign convention. So what we get is using sign convention. Okay, let's consider OB. Incident ray is along this direction. This is the direction of the incident ray. So all the distances from the optical center measured along the direction of the incident ray are to be assigned positive side, and against the direction of the incident ray are to be assigned negative side. So its focus is virtual. So OB, OB dash, OF, all are measured in a direction opposite to that of the incident ray. Therefore, all are negative. So OB is equal to minus U, OB dash is equal to minus B, and OF is equal to minus F. The focus of a concave lens is negative. So whenever it is placed in some rarer medium, so its focal length is always negative, right? So it's virtual. So let's substitute these values over here. What do you get? OB dash, that is minus U divided by OB minus U, it is equal to OF minus F minus OB dash minus V divided by minus F. So let's solve it. V by U, it will be equal to minus F plus V divided by minus F. On cross multiplying, we get minus VF is equal to minus UF plus UV, or UV is equal to UF minus VF. Rearranging the terms, we can write it like this. And students, you remember in the last step, we divide throughout by UVF. So what we do is dividing throughout by UVF. Dividing throughout by UVF. So we get 1 by F is equal to 1 by V minus 1 by U. This is lens formula for you. So the same formula is valid for concave lens as well, right? This is known as Magnification of Lens Formula. It is a mathematical relationship between the object distance, image distance, and the focal length, all measured from the optical center of the lens. So students, we can make use of this equation 1 so as to obtain the expression for the linear magnification as well. So let's do that. So directly we can make use of sign convention in equation 1. So what we get is, okay, A dash B dash. This is the image, this is the size of the image H2. Now look, it is erect, the object obviously is erect, so both are measured perpendicular to the principal axis and in the upward direction. So both are to be assigned positive sign. So A dash B dash, it will be equal to plus H2. AB being erect, it is plus H1. OB dash, it is minus B. OB, it is minus C. So what do you get? H2 by H1 is equal to V by U. And students, you are aware, the ratio of the size of the image to the size of the object is known as linear magnification. So this is the expression for the linear magnification. Clear? So in case of concave lens, we have both mathematically derived the lens formula as well as the expression for the linear magnification. So before we start with the numericals based on lens equation and linear magnification. Let's recapitulate some important facts between mirror and lenses. Students, there shouldn't be any sort of confusion between mirrors and lenses. Every concept should be crystal clear. So, let us revise those topics so that you don't get confused. So, what we'll do is, we'll prepare 2 columns and then we'll discuss the related concepts, right? So suppose this is in case of mirrors. Let's dedicate the first column to mirrors. And here for lenses. Okay. First and foremost point. In mirrors, student, when light is incident, then what happens? It bounces back into the same medium. So, reflection. So, in mirrors, reflection takes place. And not refraction, right? Obviously, when light gets incident on a mirror, partly it will get reflected, partly it will get absorbed, right? But refraction will not take place. So in mirrors, reflection does take place. While in the case of lenses, that is light traveling from rarer to denser, that is from air to lens which is made up of glass, what happens? The path of the light gets bent. And as you are aware, students, this phenomenon of bending of light or the phenomenon of change in the velocity of light is known as refraction. So in the case of lenses, refraction takes place. Refraction takes place. Okay. Now second, in case of mirrors, students, just remember, if the image is formed on the same side as that of the object, then a screen can be placed at that position and the image can be obtained on the screen. So in case of mirrors, real images are formed on the same side as that of the object. So, real images are formed on the same side as that of the object. Right? Like this is a mirror, whether you consider concave mirror or convex mirror doesn't matter. And this is F, this is C. So if an object is kept over here, its image will be formed somewhere over here. So if you place a screen, then its image can be obtained. So what I mean to say is that in the case of mirrors, the image, real image is formed on the same side as that of the object. This is the object and this is the image. Is it clear? While in the case of lens, this is a lens. Suppose here object is placed. So in case image is formed over here, then a screen can be placed over here and this image can be obtained on the screen. So I hope you have got the basic difference. In the case of lenses, real image is obtained on the opposite side as that of the object. Opposite side of the object. Right? So this is the basic difference. There shouldn't be any sort of confusion. Students, in case of mirrors, the real images are always formed on the same side as that of the object. While in case of lenses, the real images are to be obtained on the other side as that of the object. On the other side as that of the object. Right? Okay. Let's consider next case. What about virtual images? In this case, virtual images are formed like this. This is O, this is F. If an object is placed over here, its virtual object is formed, virtual image is formed like this. This is the object and this is the image. So basically in mirrors, virtual images are formed behind the mirror. While in the case of lenses, virtual images are formed on the same side as that of the object. So in mirrors, virtual image is formed behind the mirror. While on the other hand, in the case of lenses, like there is a convex lens and there is the optical center, there is the focal. Suppose an object is kept over here. So here its virtual image is formed. This is the object and this is the image. So here virtual image is obtained on the same side as that of the object. So over here virtual image is formed on the same side as that of the object, on the same side as that of the object, and therefore it can't be obtained on the screen. So students, these are some very important facts. There are some other differences as well. Let's discuss those differences also. Now, the relationship in U, V and F in case of mirrors, that is known as mirror formula. And mirror formula is, you are aware, it is 1 by V plus 1 by U is equal to 1 by F, right? So fourth point, what about mirror formula? Mirror formula is 1 by V plus 1 by U is equal to 1 by F. This is mirror formula. And just now we have discussed lens formula. Lens formula also connects, or rather it is a relationship in U, V and F. But for lens, the formula is 1 by V minus 1 by U is equal to 1 by F. That's lens formula. Right? Then, linear magnification. In both cases, it is defined as the ratio of the size of the image to the size of the object. In both the cases, linear magnification is defined as the ratio of the size of the image to the size of the object. But in case of mirrors, in terms of image and object distance, it is minus V by U. While in case of lens, it is plus V by U. Right? There shouldn't be any confusion, students, right? Do study these topics very carefully. Okay, next one. In case of mirrors, there are two types of mirrors, concave and convex mirror. Concave mirror is known as a converging mirror. Concave mirror is known as a converging mirror. While convex mirror, it is known as a diverging mirror. It is known as a diverging mirror. Right? While in the case of lenses, we have discussed concave lens. It is known as a diverging lens. It is known as a diverging lens. While on the other hand, convex lens, it is known as the converging lens. So these are essentially some very important comparative study between mirrors and lenses. So students, I must tell you, there shouldn't be any sort of confusion. In case of a numerical, just try to understand the numerical, whether it is the case of mirror or lens, then apply the appropriate sign convention, and then using appropriate mathematical formulae, we can solve it. So in the next lecture, what we will do is, we will discuss some numericals based on lens formula and linear magnification. And we need to also discuss regarding the power of a lens. But we will discuss those topics in the next episode. Till then, do take very good care of yourself and study well. Thank you.